So continuing now, we'll look at Chapter 7. This first part involving the confidence interval of sample proportions is from Section 7.1. If you're not quite sure what a confidence interval is, that's totally fine. I know the concept was maybe not as well explained in the notes in some of the videos posted on Canvas. So I did post to our Google Classroom 2 videos that help talk about the conceptual ideas of what a confidence interval is, so you can have a better understanding of what it is that you're actually calculating. So there's a lot of key formulas that came up in section 7.1. So the first one is what we call the sample error. So essentially what a confidence interval is it's an interval in which we believe that the true proportion of our item of interest, right, like the percentage of people overweight or some sort of statistic like that, the true population statistic will be in that interval. So there is going to be some error, some wiggle room to the left or less than that true population parameter, and then also above. So that's what our confidence interval is it's our estimated sample proportion, either subtracting the error amount or adding the error amount. So that error amount is going to be a z-score, what we call our z alpha over 2. And that's going to be set based off of the level of confidence. So here I did a nice little table for the common confidence intervals that you'll be asked in questions. So if they say a 90% confidence interval, you could look that up in the chart. I find that we use these same values so frequently that's helpful just to have note of those common values so you don't have to look them up every time. So if they say a 90% confidence interval, you can just use the z alpha over 2 of 1.645. If they ask for a 95% confidence interval, your z alpha over 2 is 1.96. And if it's a 99% confidence interval, then the z alpha over 2 would be 2.575. So I just like to have these written down and hand in my notes so I don't actually have to look up those values in the table every time. And then you're going to multiply that number by the square root of your sample proportion multiplied by its complement, 1 minus the sample proportion. Sometimes they call that Q hat. It's the same thing, all divided by your sample size. So I didn't write it out here, but I can do that for you now. So that sample proportion, P hat, that's just the number of values that are observed in our sample divided by the total sample size. So for instance, if I was looking at 100 customers that visited a store and I wanted to know how many bought eggs, I could observe that 20 bought eggs out of the 100. So I would do 20 divided by the 100 to get the proportion that bought eggs. So that's all that P hat is. So to build our confidence interval, I would first calculate my error separately, and then I would calculate my sample proportion P hat, and I would subtract them to get my lower bound of my confidence interval and add them together to get my upper bound of the confidence interval. I know that there's some more formulas out there that combine kind of these two formulas together. I think those just look really messy, that I prefer to calculate them separately and then just do a simple addition and subtraction to get each side of the confidence interval. Another set of formulas that are helpful is for finding the sample size. So they may say, for a 90% confidence interval, what would be the minimum sample size to know your sample proportion? So here we have kind of two ways that we need to be able to calculate it. So if we do know our sample proportion P hat, then we're going to use this formula here. So you take your z alpha over 2 based off of the confidence level that they state in the question. You're going to divide by your error. They'll have to tell you what your error is. We'll take that result and square it, and then we're going to multiply by our sample proportion and his complement, 1 minus him, or the Q hat if you prefer using the Q hat notation. The other option is if we don't know our sample proportion P hat. So in that case, we replace the second part of our equation by just the standard value of 0.25. And in both of these cases, regardless of the decimal that you get, you're always going to round up to the next whole value because any decimal amount is going to represent some part of our sample size. And even if it's like 0.01, we still want to include that. So we round up to the next whole number. So let's look at some problems that involve these formulas. So problem 23 from our test review. This is a clinical test with 1,600 subjects. 800 showed improvement from the treatment. Find the margin of error for a 99% confidence interval used to estimate the population proportion. So here they want to know my margin of error. So we're going to use our margin of error formula. So I'll go back here so we can see it. So it's the z alpha over 2 times the square root of p hat times its complement divided by n. All right, so now I need to look up the z alpha over 2. So if you don't have that handy table available that I showed you guys, you would have to look it up in the z-score chart, and that's a little complicated because you have to consider the fact that there's an extra tail bit on the left that we have to include when we look up our value. So I consider it to be just so much easier to have a handy little chart. We can just look it up here and not have to worry about looking it up on the table itself. So 99% confidence interval, that's going to be our z-score number here, 2.575. Now p hat we need to calculate as well. That is our sample proportion. So here they told us that 800 subjects showed improvement out of the 1,600. So we want to know that value. Here it's a simple proportion, it's just 0.5. Oops. So I need to put that underneath my square root symbol here. And then I do 1 minus the number. Here you could just do that in your head. It's still going to be 0.5 when I subtract it from 1, and then divide by all of my sample size, which is 1,600. So I just type this into my calculator, being very careful in how I type it in to make sure that I have all of the correct values on the top of my fraction bar grouped appropriately, and then everything's underneath your square root symbol. So you absolutely can type it in kind of like you see it on your calculator, using your different functionalities to type in fractions and square roots, but just make sure that it is typed in correctly. So let me do that now. So I can see that my error is 0.032. If you want to see how I type that into my calculator, that's what it looks like right there. So how I was able to do that, and see if I can make sure that you guys are able to see this. So I typed in 2.575. I hit second and then the square root key. And then to get the fraction set up like you see here, if you hit the green button alpha and then the y equals button, oops, sorry, wrong thing. It gives you the option to do fractions, just a shortcut to typing in fractions. So here I want option 1, n divided by d. Okay, and then you can see that it creates that editor where I can type in the numerator and denominator. So I do 0.5 times 0.5, arrow down to my denominator where I type in the 1,600. So that's a really handy way to be able to type it in all at once. I prefer doing that, typing it in all at once and just being very careful how I type it in, because I feel like I get more accurate decimals that way. All right, so now I know my error. In this case, that's all that they wanted. If they asked for the confidence interval, then we would go ahead and take our p hat and then subtract my error to get the lower bound of my interval and add the error to get the upper bound. But here they just wanted to know the margin of error, so that's it. Now looking at problem 31, it says use the given degree of confidence in sample data to construct a confidence interval for the population proportion P. 31 says a survey of 300 union members in New York State reveals 112 favor the Republican candidate for governor. Construct a 98% confidence interval for the true population proportion of all New York State union members who favor the Republican candidate. So here I need to calculate my p hat and I need to calculate my error. So my p hat is going to be the number of people in favor, which is 112, divided by 300. And we do want the decimal form of that, since that's going to be a lot easier to type into our error formula. Now here, we want to be careful about accuracy, so I don't get a nice clean decimal. So I'm just going to round it to 3 decimal places. Usually if you go to 3 or 4 decimal places, you'll be good. If they ask for more accuracy in your final answer, then of course just include more decimal places. Then for the error, we're going to use that same formula. It's the z alpha over 2 times the square root of p hat times his complement divided by the sample size. So here they want a 98% confidence. So I'm going to go back to my chart. Oops, too far. All right, now you can see here that 98 is not a common number that I have listed in my table. So this one we're going to have to look it up by hand, and that's okay. So what I'm going to do is draw myself a diagram. So when they say 98% confidence, they're saying that my p hat is somewhere here in the center, kind of like our mean, and we're going to have a value for my interval to the left or to the right, and we want the center portion to be that 98%. So to look that up in my z-score chart, we have to keep in mind that the z-score chart goes from the left. So it wants to include this extra tail bit on the left. So what I'm going to do is find the complement. So how much is not included in my 98%? Well, it's 2%. So my 2% would be distributed on both sides of my tail. So 1% would be on the left and 1% would be on the right. So if I know that my z-score chart works where it finds all the area starting from the left, I would add up the left tail and then my center portion, which means I'm actually going to look up a 0.99 value in my z-score chart in order to get that z alpha over 2 number. So looking at my chart, I'm looking for 0.99. Sorry, it takes a little while to find. Okay, so it's going to be in between these two numbers. So again, I look at which one's closest. So this one is 0.0, well, it's more than that, actually, from 0.99. So if I do 0.99 minus 0.9898, it's 0.0002 away. And if I do 0.9901 minus 0.99, this is 0.0001. So this one is slightly closer, so I'm going to use that number. So it would be negative 2.3, and then we have to scroll up there. 3. So negative 2.33 will be my z number. Okay, and then we're going to plug in our p hat and our n value. So plugging all of my values in, and then calculating this in my calculator, I got the error is 0.065. So I need to take my p hat, the 3 point, let me write this down, oops, my 0.373. I'm going to add my, subtract my error to get the lower value of my bound. And then I'm going to add it as well. So let me write that a little bit more clearly for you all. So again, to find my lower bound, I went ahead and took my p hat and I subtracted my error. That ended up giving me 0.308. And then I also took my p hat and I added my error to get the upper bound, which is 0.438. So what that means then, how we would interpret this, is we can say with 98% confidence that our true sample population proportion would be in between 0.308 and 0.438. So that would be our confidence interval there. The other thing I wanted to show you all is that this confidence interval can also be calculated on your TI graphing calculator. So I'll show you how to do the same problem there. It is always good and helpful to certainly work it out by hand, but there is the option of checking it in the calculator as well. This is only really good for calculating the confidence interval if they ask you for the error amount or the minimum sample size that's required, those are not things that you can type in automatically to your calculator. But I did want to show this as a way for you to double check your work as well. So let me show you how you would type that in. So here you would need to go to the Stat button, and you're going to go over to the right where it says Tests, and you're going to have to arrow down. What we're looking to do is a 1 proportion z-test, which is option A. So when A is highlighted, you hit enter. And then we have to enter in some information. So X represents the number of data values. Here it's the number of people in favor of the candidate. So you would just type in the number, so 112, enter. Then N is our sample size, so that would be 300, enter. And then C level represents our confidence level. So here it was 0.98. And then you're going to arrow down, so that calculated is highlighted, and you hit enter. And then it's going to give you your interval. So here we can see the interval was from 0.30837, which is the same as the lower bound that we got in our example when we worked it out by hand. And then the upper limit was 0.4383, which again, rounding the 3 places is the same as what we got in our example. So using that 1 proportion z-test, you can also calculate your confidence interval in the calculator. So I wanted to demonstrate that for our next example as well, just to practice that one more time, how to do it in the calculator. So for our next example, problem number 32 from the review, we need to gather all those key bits of information that we just typed into our calculator. So it says of 150 adults selected randomly from one town, 30 of them smoke. Construct a 99% confidence interval for the true percentage of all adults in the town that smoke. So the first thing is I need my sample size, the N. Here's going to be my total of 150. And then our X value, which represents the number of people that we're calculating the percentage of. So here it's going to be the 30% of people that smoke. And then my confidence interval amount, that's going to be the 0.99, or the 99% that they were talking about. Okay, so now let's type that into our calculator now that we know how. So let me go ahead and clear out what we had previously. So again, we go to the Stats button. You arrow to the right, so that test is highlighted, and you're going to scroll down to option A, which is the 1 proportion z-test. Hit enter, and we're going to type in our information. So it was 30 people that smoked out of a total of 150. Our confidence level was 99, so 0.99, and calculate. So that's going to be my lower bound and upper bound for our interval. If you notice, it does give you your p-hat as well. So our sample proportion was 0.2 if we needed it. And so I would just round that to the appropriate number of decimal places. So here, let's go ahead and write that down, rounding to 3 decimal places. So here the lower bound was rounding to 3 decimal places, 0.116. Upper bound, if we round to 3 decimal places, is 0.2484. And then I just wrote down the p-hat, not that we need it for this particular problem, but if I did, it was that 0.2 that our calculator gave us as well. So some other formulas that you might need as well, if they do give you a confidence interval and they need you to find the p-hat or margin of error, really all that you're doing is trying to find the middle point, or how far away the middle point is to each of our bounds. So if you need to find the p-hat, you're essentially just going to find the average of your limits. So you'll take the upper confidence interval, add it with the lower one, and divide by 2. And if you need the margin of error, you'll subtract the upper minus lower and divide by 2. So let's try an example of that, like problem 20 from our review. So here they give us the confidence interval from 0.38 to 0.54, and they want us to write it in the form of our p-hat plus or minus the error. So first we need to find our p-hat. So we're going to go ahead and average together the upper and lower bounds of our interval. So add together 0.38 with 0.54 and divide by 2. So that will give us 0.46 once we've done all of the math. And then for the error, we'll find the difference divided by 2. So I'm going to take the upper limit, 0.54, subtract my lower limit, 0.38, and then divide by 2. Here when we do the math, we can see it's 0.08. So to write our confidence interval in that form, p hat plus or minus our error, my p hat was 0.46 plus or minus the error amount, which was 0.08. Oops. The next concept that was covered in section 11.2, that involved our t-distribution, sometimes referred to as the student t-distribution. And essentially, that distribution is helpful when our distribution may not be perfectly normal, or we're not too sure that it is perfectly normal. So there are some criteria to kind of help you determine when to use the t-distribution that we'll talk about later. But for the most part, you'll have some sense that you're going to need to use the t-distribution for the problems. So the sample error, that formula is going to be a little bit different for a t-distribution, and just that we're going to be using the t alpha over 2 instead of the z normal alpha over 2. And we're going to be using our sample standard deviation divided by our sample size. So keep in mind the critical value, that t alpha over 2. That's the area in the t-distribution that's separating alpha over 2 area on the right side. I know in the course videos they suggested you using the calculator to look this up, and then there's also a t-table as well. Both of those are perfectly fine options to find your t alpha over 2 amount. If you do use the table, then you're going to need to look it up based off of the degrees of freedom. Those degrees of freedom are just your sample size subtracted by 1. If you need to find the confidence interval, similar to what we saw for a proportion, p hat, you're going to take your sample mean and subtract the error amount that you calculate to get the lower bound of the confidence interval, and you'll add the error amount to your sample mean to get the upper bound. Note, this can also be done in the calculator as well, and I know that there were some videos showing you how to do that in the calculator. One formula, if you need it, if you do need to find your t value, kind of like how you find your z value in the normal distribution, this would be the formula that you use. So you're taking your sample mean, subtracting the population mean, and then dividing by your adjusted standard deviation, which is your sample mean divided by the square root of your sample size. So in this section in particular, there's a lot of videos on how to do this in your calculator. Here's a cheat sheet, how to get your t alpha over 2, and then also how to find your t confidence interval on the calculator. So if you do need your t alpha over 2 to be calculated, you can press the distribution key, select option 4. You need to type in your area that you want, which here you would calculate by doing 1 minus your alpha over 2 area, and do your degrees of freedom. Once that's all been typed in, you can press paste and then enter, and that'll calculate your t alpha over 2 for you, so you don't have to use that t distribution chart. If you want to calculate your confidence interval, these would be the steps that you go through, and we'll actually do this here in a moment, so I won't read off the steps for you all. So problem 36 from your review, we want to use the given degree of freedom and sample data to construct a confidence interval for the population mean, mu, and assume the population has a normal distribution. So a laboratory test 12 chicken eggs and found that the mean amount of cholesterol was 185 grams with a sample standard deviation of 17.6 milligrams, and we want to construct a 95% confidence interval for the true mean cholesterol of all eggs. So here we want to use the sample t-distribution because we have the sample standard deviation given to us, right? We don't have the population standard deviation. But also too because we know that the population is coming from a normal distribution. So we need to know that wherever we're getting our sample values from, that they're coming from an ultimately normal distribution as well. That's a key criteria. So the setup here, we could calculate our error with the formula, and I'll show you guys how to do that first, and then we'll do it with the calculator as well. So the error formula was the one that we saw previously. So it's our t alpha over 2, and we're going to take that and multiply it by our sample standard deviation divided by the square root of our sample size. So some of this we can fill in already. We know our sample standard deviation is 17.6, and we know our sample size was 12. So what's missing is our T alpha over 2. So here we want the 95% confidence interval. So the alpha is the complement of that. It's 1 minus the confidence interval amount that they gave us. So it's representing the value in the tails of our distribution. So here that's 95%. Now here you can see it's alpha over 2 because what we're really describing here is my true mean, right, is going to be somewhere in the middle of my distribution, and we want to have 95% of our interval to be covered, or 95% confidence to be covered in my interval on either side. And so that 5% is going between my two tail ends, the tail on the left and the tail on the right. But the way that our T distribution is set up is like the Z distribution. It has the values from the left. So I'm going to take that 5% that represents both tails, and I divide it by 2 to figure out what just the left tail piece would be. So that would be 2.5% or 0.025. So the true area that I'm looking for underneath my T distribution here would be the 0.95 added with that extra 2.5%. Or in total, 0.975. So that's what we're looking for, is what is the T value that creates that area underneath our curve of the 0.975. So you can look it up on your T chart, so we'll do that, and then I'll also show you how to do it in the calculator. So this is our T distribution chart. So if you can see along the top here, the 0.975 that I talked about is this column. So I can also just use, if you notice this chart also has the confidence intervals at the bottom. So I could have kind of skipped that step of figuring out what the 0.975 was by using this number on the bottom. But I just want to give you guys context where the number was coming from. So you could either do that alteration like I did to figure out the probability value from the left here on the top, or this one's really handy. You could have just looked at the 95% confidence interval along the bottom. Now the other thing that I need to know is my degrees of freedom. That's the values here along the left. So our sample size was 12. We had 12 eggs, but our degrees of freedom would be 1 less. It would actually be 11. So I'm going to look at the row that has 11 and then the column that represents our 95% confidence interval. So here I end up getting the number 2.201. So that's our T alpha over 2. Now let me show you how you would do that same process in the graphing calculator. So here what we're going to do, let me actually clear this out. Oops. Is you're going to go to the distribution button. So you have to hit second and then the vars button. So second vars will get you into distribution. And we want option 4, which is the inverse T. And then you have to type in this information. So I already typed it in, but we would need to calculate the area on the left. So like how I showed you to get the 0.975, we would have to do that calculation. So that's the one drawback to using the calculator compared to the chart. Degrees of freedom, we have to take our sample size and subtract 1, so that's where our 11 came from. And then if you hit paste, it'll paste it into your home screen, but you still have to hit enter to actually perform the calculation. So here we can see if I do round it to 3 decimal places, the 9 would round up my next digit to a 1. So I still get the 2.201 using the calculator as well. So when I type in all those values to my calculator, I'll get that my error is approximately 11.18. So now to construct our confidence interval, we need to take the error amount and subtract it and add it from our sample mean. So here they told us that the mean amount was 185. So I'm going to take 185 and subtract my error amount to get the lower bound of my confidence interval. So when I calculate that, I get 173.82. And then we need to calculate our upper bound. So the upper bound of my confidence interval is going to be my mean added by the error. So we're going to take 185 and we'll add our error amount. So calculating that, I get 196.18 as my upper bound. So those are the values for my confidence interval. So how we would read that off is we would say that there's a 95% confidence interval, that our true mean for the cholesterol contents of all eggs would fall between 173.82 milligrams and 196.18 milligrams. Now this is us calculating everything by hand, but we can also calculate it in our graphing calculator, and that is what I'll show you right now. Okay, so in our graphing calculator, we're first going to go to the stat menu. So you hit the stat button, arrow to the right so that you're under tests, and the option that we want is the t-interval, which is option 8. Now here you have two options. There's the option to use data. So in other words, if I had all of my data values and I wanted to type them all into my stat edit menu and listing them all out, then I could use that and it would calculate my mean and standard deviation from the raw data. Here we actually have the statistics. We know the sample mean and standard deviation. So you want to make sure that the stats option is highlighted, and then we can type in our values from here. So the sample mean was 185. Then our sample standard deviation was 17.6. Our sample size was 12 eggs, and our confidence interval was 95% or 0.95. So once all of those have been typed in, you're going to highlight calculate and hit enter, and then it'll calculate your confidence interval from there. So here I can see that it does match the interval that we found previously from 173.82 to 196.18. So another option is to do it in your calculator. Some additional formulas from section 7.2 is for finding the sample size in our t-distribution. So here it's going to depend upon whether or not we know our standard deviation for the population. So if we do know that standard deviation, then we're going to use this first formula. So you're going to find your critical value, the z alpha over 2. You'll multiply it by your standard deviation for the population, divide by your error, and then the results of that division you'll go ahead and square. There are some cases when the standard deviation is unknown though. I know there was a problem on the homework like this. And how you would do that is you need to use the rule, the range rule of thumb, which is that your standard deviation can be approximated by your range or the number of values that your data covers. So you would find that by calculating the highest value in your data set minus the lowest value in your data set. That is your range, and you'll divide it by 4. So it's the exact same formula. All that I did here is I replaced our standard deviation, since we didn't know that, with the range rule of thumb. So you would take the range and divide by 4 instead. So here let's try out an example from our review, number 38. We want to calculate the minimum sample size to estimate the unknown population mean mu. So how many commuters must be randomly selected to estimate the mean driving time of Chicago commuters? We want to find the 90% confidence that the sample mean is within 4 minutes of the population mean, and the population standard deviation is known to be 12. So let's write out the information that we know. So we know our confidence interval amount is that 90%. They said they want the sample mean within 4 minutes, so that within part is referring to our error. We're allowing an error of 4. And then our standard deviation is known to be 12 minutes. So we do know our standard deviation is 12. So we're going to go back and look at our two formulas to determine which one is the option we want to pick. So since I do know my standard deviation, we're going to use this top option. So we're going to take our z alpha over 2, multiply by my standard deviation, divide by the error, and square it. So my z alpha over 2, this you could look up in your z chart, or I did give you guys that handy reference chart in your notes when we talked about our confidence intervals for proportions. There is the 90% one that's there that's pretty handy. So let me go look that up. So looking at my chart here, the 90% confidence interval, my z alpha over 2 would be 1.645. Now that we have our critical value, now we can go ahead and plug in the rest of our information. So our standard deviation we know is 12 and the error is 4. So we'll type that into our calculator and get our value for our sample size. Typing that all into my calculator, I get 24.35 and so on. Now here the rule of thumb for sample size is any decimal amount, even if it's really small, like 0.001, whatever, any decimal amount has to get rounded up for this sample size. So this would automatically round up to 25. So we'd have to survey 25 people to meet our criteria. Similar to what we saw for our proportion confidence intervals and needing to find the point estimate for p hat and the error, a similar thing may happen for us on our confidence intervals here, that they may give me the confidence interval and I need to find my x bar and my mean, and my error. So it's essentially the same formula. You would take your upper limit and lower limit of your interval, add them together and divide by 2 to get your x bar, and then to get the margin of error you would take the upper limit minus the lower limit and divide by 2. The last thing for us to review is which proportion to use now that we've looked at the t distribution and the z distribution, knowing which one to use in different circumstances. So for the t distribution, we generally use that when our population standard deviation is not known. So that's kind of the key thing there, is if we don't know our standard deviation of our population, then we have to use our student t distribution. One other key criteria though is that our population should be normally distributed no matter what, and ideally we want to have or if it's not normally distributed, to have our sample be greater than 30. So those are kind of the two criteria. Either they say that the sample came from a normally distributed population, even if the sample size is smaller, or our sample size is bigger than 30. For our z distribution or normal distribution, the key thing is that our population standard deviation sigma is known. It should still be normally distributed, of course, or we do know our standard deviation and the sample size is bigger than 30. And then the worst kind of case is that our population is not normally distributed and our sample size is small. So if those happen, then you need other methods that we haven't yet looked at, called bootstrapping. So here, for the purposes of your exam, you're either going to need to use the t distribution or the z distribution. So here are some key things to know. So the z distribution, we use our z-scores. The t distribution, you would use this t-score, which essentially just has that altered standard deviation, since we're using the sample standard deviation. Our error is very similar. The only difference is I'm using the t distribution for the t alpha over 2 compared to the z value for alpha over 2. And then our confidence intervals are going to be built the same way. You would take your sample mean and add or subtract your error for your confidence interval in a t distribution. For a z distribution, you'll take your population mean and add or subtract your error. So let's practice identifying which distribution to use. So problem 39 and 40 from your test review are good for that. So it says use the confidence interval and sample data to find a confidence interval for estimating the population mu, round your error to the same number of decimal places as your sample mean. So for 39, we know our test scores. We know a sample size is 72. Our sample mean is 58.1. Our standard deviation is 6.2 with 98% confidence. So here, because I do know my population standard deviation, that means that I can use my normal distribution and my z-scores. So here I want to do a z interval. And that one we can do pretty easily in our calculator, so I'll show you how to do that just to condense some steps. All right, so to do our z-interval in our calculator, you're going to again go to your stat menu. So I'm going to press the stat button, arrow to the right to tests, and this time I'm going to select option 7, which is the z-interval. So again, I can see I have the option to enter my data or just enter my statistics. Since we already know our sample mean and standard deviation and all that, we want the statistics option, and we're going to type in our values. So my population standard deviation is 6.2. My x-bar, our sample mean, is 58.1. My sample size is 72. And the confidence interval, we want 98% or 0.98. So once you've typed all your information in, you're going to highlight calculate and hit enter, and that will give you your upper and lower bound of your interval. So it's going to go from 56.4 to 59.8. So here I'm just going to write down my result. So that would be how we would write our confidence interval. How we would read it in words is we would say that we're 98% confident that the true population mean would fall between 56.4 and 59.8. Now looking at number 40, we have 37 packages are randomly selected from packages received by a parcel service. The sample has a mean weight of 10.3 pounds and a standard deviation of 2.4 pounds. What is the 95% confidence interval for the true mean weight mu of all packages received by the parcel service? So here let's write out what is known. So we know we have 37 packages, so that is our sample size. We have our sample weight, that's our x-bar of 10.3. And we have our sample standard deviation. And our confidence interval was 95%. So here, you have to read it very carefully, but the standard deviation that they gave us was for our sample, right? So that's our S, and not our population standard deviation. So in this case, because I don't know the population standard deviation, we can't use our z-interval anymore. Now this is going to be a t-interval. So the other criteria would be to determine whether or not it's a normally distributed population that we're pulling from. Here they never mention that, but that's okay because our sample size is large enough. It's larger than 30, so it does meet the requirements that we were considering. So here if we look, my population standard deviation is not known. We don't know whether or not it's normally distributed, but we do meet the requirement of being greater than 30. So we're going to use a t-distribution for this calculation. And again, we could do this by hand, like how we have in the past, but I'll go ahead and just show you how to do it on the calculator one more time to make this a little bit faster. Okay, so again, we're going to go back to our stat menu. We're going to arrow to the right to tests, and this time we want the t-interval, which is option 8. We want the statistics because we know the statistics here. I'm going to type in my x-bar, my S, and my sample size. So typing all of that in, so our mean was 10.3, sample standard deviation 2.4, our sample size 37, and our confidence interval 0.95. There is our interval. So rounding to 1 decimal place, which they wanted, since that's the same number of decimal places as our mean, we would have our interval from 9.5 to 11.1.